Okay, so I'm going to go ahead and talk about the kind of an application of the rate laws that we were talking about last class. Okay, so on this video, I'm going to talk about the integrated rate laws, how we're going to use them, and then I'm going to go over the half-life expressions. So this is kind of like the middle of the presentation that I have up online. Okay. All right, so we introduced you guys to the rate laws last time. Okay, so last class we talked about rate equal to k, and then a, and this a is usually raised to some power, right? So this is what we called the rate law. And there were a couple different things that came out of it, right? So k was something called our rate constant. It was a constant as long as we're at a specific temperature. When we're talking about A, this is concentration of usually our single reactant type of reaction, all right? So our single reactant, and then N was called our reaction order, okay? And so N could be a 0, a 1, a 2. It could be other things, but these are the most common values for N, right? So if N was equal to 0, that was 0 order reaction. If N was equal to 1, it was first order. N was equal to 2, it was a second order reaction, okay? So again, this is what we mean by rate laws. And we also could only determine these rate laws experimentally, right? So we could go in, we could manipulate our concentrations of A, we could measure the rate, and we could get the orders of our reaction from that, okay? So now, an application of these rate laws are what are called the integrated rate laws, okay? So this is going to take our rate law and kind of manipulate it so that we can answer a couple of other questions that we would like to, okay? So if we look at the rate law as it is right now, there is no time dependence in this at all, right? So we have rate is equal to concentration of reactant times K, and there's no time dependence. But a lot of times we would like to know how the concentration varies as a function of time, right? So a good example of that are these guys, these things called CFCs, these chlorofluorocarbons. So these things were used in refrigerator systems back in the day. And the only problem with them, they were very good at their job, but the problem with them was as they escaped into the atmosphere, they essentially led to the overall destruction of our ozone, okay? So that's bad. We need the ozone layer to protect us from harmful rays. And so a lot of regulations went into place to kind of phase out the use of these chlorofluorocarbons. The problem with that, though, is that they have very, very long lifetimes, right? So there are CFCs that are still in our atmosphere from 20 to 30 years ago because they have an overall atmospheric lifetime of 45 years or 100 years, etc. Okay, so even though we're not putting them in the air today, they're still up there and they're still doing whatever type of damage. So it would be helpful to be able to know, in 20 years' time, how much of our CFC 11 is going to be left, or how much of CFC 12 is going to be left. Right now, with what we have learned, we aren't actually capable of doing that. But with the integrated rate laws, we are going to be able to determine how much of something is left given a certain amount of time has passed in a reaction, and vice versa. If we want to know, this went from 1 molar to 2 molar or whatever, how long is it actually going to take to do that? Okay. So, what are the integrated rate laws, and how do we come about them? Okay. All right. So, the problem with the integrated rate laws is, number one, they're very difficult, and I'll kind of show you how we derive them just very briefly, but they're very difficult to derive for any type of reaction that has more than one reactant. Okay, so when we talk about these integrated rate laws, we're always assuming that we're dealing with reactions that only have one reactant, because if they had more, the derivation of these laws would get too much and we wouldn't actually be able to do anything with them. Okay, so all of these guys are assuming that we have only one reactant in the reaction, and each integrated rate law is going to depend on the order of the reaction, right? So each reaction order, whether it was going to be a 0 order, a first order, or a second order, they're all going to have their own integrated rate law, because they're all going to be derived from the original rate law, okay? So I know that doesn't really make any sense. Hopefully I'll illustrate it in a second, all right? Okay, so we're going to start by talking about the first order integrated rate law, okay? So this is for reactions that are first order. So again, we're assuming that we have a reaction where we have a single reactant going to make product, okay? And this single reactant is first order with respect to this guy. So the rate law for that, we know, is rate is equal to K, the rate constant, times the concentration of A to the first power, because it's first order, okay? We also know that we can measure the rate of this reaction from the rate expression, right? This is just going to be the negative change in concentration of A over change in time. That's what we learned on how to initially measure rate. Because A is a reactant, we put a negative in front, right, to make sure that that is positive. Okay, so what we're going to do now is we're going to combine this guy and this guy, right? Because rate is equal to this, rate is also equal to this. So we're going to set them equal to one another, and we're going to be left with something that looks like this, okay? Another way that we can write this, if you're super into the calculus and the derivation of this, is instead of these change in, we can also use the D, oh no. We could also use the D notation. So D concentration of A over DT is equal to K concentration of A. Now what we're going to do is a bunch of little steps called, again, calculus. So we're going to take this, we're going to separate the variables. So we're going to separate the dAs and the As and the dTs. We're going to put them on different sides of the equation, and then we're going to integrate. And this is what we mean by integrated rate laws, okay? If you're interested in how we go from this guy to what this is, the calculus involved, please ask me at some point in time. I'm not actually going to show you that derivation, okay? But just trust me, we take this, we do math that actually exists, and what we are left with is this, which is the first order integrated rate law, okay? All right, so there's a lot of little different letters, a lot of different terms in here that I'm going to explain, okay? So ln is the natural logarithm. Okay, so just note ln of A is just the natural logarithm of A, and this is a concentration of A at whatever time we're interested in. This is equal to minus K, which is still just the rate constant, times T. T is just the time. This is where our time portion comes in, plus the natural logarithm of the initial concentration of A. So this A naught is initial concentration. Again, something that we can usually control, all right? So you will hopefully notice that this kind of takes on the form of a straight line equation, right? We have a dependent variable, okay, so concentration of A is equal to something times a time, right? And time is going to be our independent variable. This is going to be our x, okay, plus something else, okay? So hopefully you note that this kind of takes the form of y equals mx plus b, where y would be the natural logarithm of A. X is time. M is our slope, which is going to be minus K, minus the rate constant. And then the y-intercept ends up being this natural logarithm of initial concentration of A. Okay, so what does this all mean? So let's say that you went out and you did an experiment where you measured the concentration of A as a function of time, right? That's something that you can do, okay? And you got a bunch of different values, okay? If you then took the concentration of A, if you took this guy and instead plotted the natural logarithm of that data, right? Because you can just push in a number, push in natural log, it transforms it. So you get a bunch of data, and if you plotted this as your y and this guy as your x, what you would get is a straight line, okay? And that line would be this guy. The slope of that line, oh no, not my pencil too. The slope of that line, so m would be equal to the minus rate constant. So if you wanted the rate constant, you would just take the negative slope, and the y-intercept would be the initial concentration of A, okay? So this is a way that you could have data that you can measure, concentration time data, you could transform it, and you could figure out a rate constant as well as an initial concentration from that, okay? Okay, so that's a lot, right? But just note that if you had a bunch of data and you plotted the natural logarithm of concentration as a function of time, you got a straight line that would indicate that it was a first order reaction. We also utilize this to kind of figure out what order these reactions are. Okay, so that is first order. We also have a completely different one for second order, and it comes about in the exact same way. So the rate law for a second order reaction is rate is equal to K times concentration of A raised to this 2, because this is second order. And then the measurement of rate, again, comes from the exact same rate expression. Same type thing. We're going to set these guys equal to one another. And now, again, calculus happens. And instead of getting the ln thing, we get in a completely different equation with respect to this second order integrated rate law. So now this is 1 over the concentration of A is equal to KT plus 1 over the initial concentration. Okay, and again, this takes the form of a straight line equation where the y is 1 over concentration and the x is time again. Okay, so now the slope is directly equal to the rate constant, and the y-intercept is 1 over the initial concentration. Again, how would you actually utilize this? So someone went in, measured concentration versus time data, and they transformed that by taking the inverse of the concentration. They plotted it as a function of time, and they got a beautiful little straight line, which indicated to them that this was a second order reaction where the slope is equal to the rate constant, okay? And the y-intercept is 1 over the initial concentration. Okay, so that is second order. Finally, the last one is zero order, which you don't encounter all that often. This is kind of like the least important of the bunch. Again, though, we derive it the exact same way. So the rate law for a zero order reaction is given here. We're going to set this guy equal to our rate expression again. We're going to be left with this. Calculus, again, is going to occur. And then we're going to be left with our zero order integrated rate law, which is just concentration is equal to minus K times T plus initial concentration. Okay, so this guy is our Y. Our slope is minus K now, T is our X, and then initial concentration is our Y-intercept, okay? So again, this would again just be like someone going in, being like, I measured concentration data as a function of time, I plotted it, and it gave me a straight line directly. I knew this was zero order because of that, and the slope is equal to minus K, so if I wanted the rate constant, it would be minus slope. Okay, y-intercept, again, is just directly the initial concentration. Okay, so how are we actually going to use these? Because this is all like in just a void by itself. They don't really necessarily make sense. So let's show how we would actually utilize these integrated rate laws in an example. Okay, so in this example, we have this reaction. Again, it's a single reactant reaction. And they tell us that a plot of the natural logarithm as a function of time, so ln of A versus time, yields a straight line. All right, so that's a big indicator right now that this, because it's ln of A versus time, is a first order reaction. If it was something like second order, they would say 1 over the concentration versus time. 1 over the concentration versus time was straight line. It didn't say that. It said ln of A versus time. So if it said this, this would be second. It doesn't say this, so it's first, okay? That's probably not the best way to explain that, okay? But again, this thing right here, ln of A versus time yields a straight line. That's a big indicator that this is a first order reaction, okay? Now, they also tell us the slope. The slope has a value. So m has a value of minus 0.0045, and then this units here are seconds inverse, okay? So the first question they ask is, what is the value of the rate constant for this reaction, okay? We know that we got a straight line when we plotted ln of A as a function of time. So from this, ln of A is equal to minus kt plus ln of A naught. If we wanted the y-intercept, they would need to give us the y-intercept. Instead, we want the rate constant, and we know for a first order reaction that the rate constant is just going to be the minus slope, right? They give us the slope of the line, so the rate constant is just going to be the minus 0.0045 seconds inverse, which gives us a positive 0.0045 seconds inverse, okay? Again, rate constants have to be positive. So when we transform this, we end up getting this decreasing slope. We get this negative slope. It can't ever be negative, so that's why it's a negative times a negative, which gives us a positive overall, okay? A couple other things to note. The units here are inverse seconds. If the reaction is first order, then the units for the rate constant will always be inverse seconds. And again, that can be derived directly from the rate law. You don't necessarily have to be aware of that. Okay, all right. So now that's A. What is the rate constant? We've written it. B, they want us to write the rate law for this reaction. Okay, so we know it's first order. There's only one reactant. So the rate law is just rate is equal to K. We actually have a value, so we can plug that in. 5 inverse seconds times the concentration of A to the 1. Okay, that is the rate law. That is it. And then C, this is when we're actually going to utilize these integrated rate laws in the way that I kind of introduced them, right? So for C, they say for this reaction, if it had initial concentration of 0.25 molar, what is the concentration after 225 seconds? So this is what I mean by how does the concentration vary as a function of time, and can we calculate that type of data, right? So this is what these guys are for. Ln of A at whatever time we're interested in is equal to minus KT plus ln of A naught, okay? What we want to know is this guy. We're solving for this guy, and we know everything else in this equation, okay? So I'm going to go ahead and leave this guy as ln of A. When I use this little t subscript, I'm just denoting this is the concentration at whatever time we're substituting, right? We actually know the time that we're substituting here, so I can maybe even remove this t and say the concentration at 225 seconds. You don't have to do that, but again, this is not a variable or anything. This is kind of just like a notation of what we're actually looking at, okay? So ln of A is equal to minus K. So K we have over here 0.0045. I want to move this down because it's going to get stuck. Okay. All right, so ln of A at 225 is equal to minus 0.0045 seconds inverse times t, which is the time that we're solving for. So this is 225 seconds. The only thing to note here is making sure that our units are correct. Sometimes they'll give you time in hours and you'll have to convert, but the units are correct here, so we can just plug it in directly. Plus ln of initial concentration of A. They told us that the initial concentration was 0.250 molar. Okay, so now we've got a bunch of numbers. All we need to do is plug stuff into our calculator and solve for things, okay? So this stuff, so 0.0045 times 225 gives us a minus 1.0125, and we're going to add to that 0.255 natural logarithm of that, which ends up being a minus 1.3863. This is equal to ln of A. Okay, so I'm going to add these two together. I get minus 2.399 is equal to ln of A. And then to isolate A by itself, to get A alone, all I have to do is e raised to both sides. So e raised to this side, e raised to this side gives me A is equal to 0.0908 molar. And so this is the concentration of A at of A at, that's not of A at, of A at, of A at 225 seconds. And intuitively it makes sense. It's less. We started at 0.25. It's gone down to 0.09, so that makes sense that it went down and that it went down of that magnitude. Okay? So that is how you would utilize a problem like that. I would expect on the quiz, same exact thing most likely, except I probably will change some numbers with respect to some of the datas. So be comfortable utilizing this guy with respect to solving problems. Okay, so then on question 14.4, it's similar type thing. We have a one reactant reaction. So our one reactant is our AB here. So we're looking for a rate law where rate is equal to K times the concentration of our single reactant raised to some power. And they've taken some concentration versus time data, and what they found when they did that is when they plotted 1 over the concentration of our reactant as a function of time, they got a nice straight line, and that line had a slope equal to a positive 0.55 units of inverse molar inverse second. Okay, so this 1 over concentration as a function of time, that giving you a straight line, is a big indicator that this is a second order reaction. And in a second order reaction, the integrated rate law is 1 over AB is equal to K times T plus 1 over AB initial, AB naught. So the slope is our rate constant, and it's directly equal because there's no plus or minus or anything here, right? So on part A, they ask us what is the value of the rate constant. Well, that's just equal to the slope of the line that they get. So K is equal to a positive 0.55 units of inverse molar inverse seconds. And then also something to note, anytime that your reaction is second order overall, the units of K will be 1 over M, 1 over S. So inverse molar inverse second, or 1 over M times S. But again, that's for second order overall, and that can again just be derived back from the original rate law. Rate is equal to K AB raised to the second power. Right? These units, K's units, can always be derived just back from the original rate law. All right, so then in B, if the initial concentration of AB, so AB 0, AB naught is equal to 0.150 molar, what is the concentration after 0.5 hour? Okay, so this is when we would actually utilize this integrated rate law and solve for the concentration after a half of an hour, right? So this is concentration at whatever time we're interested in is equal to K T plus 1 over initial concentration. We know K, all right? So we're solving for this guy. We can go ahead and start plugging some stuff in. So AB at time T is equal to K, which was 0.55 inverse molar, inverse seconds, times T. Now the problem here is that T is in 0.5 hours, right? So I'd mentioned this on the example. Our units here are in seconds, so we need to convert 0.5 hours to seconds, right? So for every 1 hour, there are how many minutes? So 1 hour is, 60 minutes, and then in every 1 minute, there are 60 seconds. So 60 times 0.5 ends up being 1,800 seconds. Okay, so I'll go ahead and plug that in, 1,800 seconds, plus now 1 over the initial concentration, which is 0.150 molar. Okay, so now I can start solving for things. I have 1 over AB is equal to 0.55 times 1,800 gives me 990 plus 1 over plus 1 over 0.150 is 6.667. When I add those two together, I get 1 over AB. Is equal to 996.7. And then this isn't the answer. A lot of people always like to stop here. We want just AB by itself. So to solve for AB, we're just going to take the inverse of this number. So I'd multiply both sides by AB, multiply both sides by AB. That would get rid of this, and I'd have 1 is equal to 996.7 times AB. Then just to solve for AB, you would divide both sides by 996.7, divide by 9. Okay, it's nice and sloppy. Divide by 996.7, right? And so AB at half of an hour ends up being equal to 0.00100 molar. When we were up here, I went through like the entire process of seeing how you would solve for AB, multiply both sides by AB, and then redivide by the number. You could also have just taken the inverse of 996.7. Sometimes there are calculator buttons, a button on your calculator actually that will just take the inverse of whatever number you're interested in. Okay, so that is how you would utilize the second order integrated rate law. Okay, again, with respect to the quiz, I'd be comfortable with solving problems like both of these. Okay, so in the second half of this video, we're going to talk about kind of another expression that you can derive from the integrated rate law, and it is a specific expression. It's called the half-life, okay? So the half-life is defined as the amount of time it takes for the initial concentration to drop to 1/2 of its initial percent, right? So, for example, if you had 1 molar initial concentration, and let's say its half-life, which we denote as T with the little subscript 1/2, is equal to, let's say, 100 seconds. That is telling you it will take 100 seconds for this thing to go from 1 molar to half of 1 molar, or 0.5 molar. Okay, so that's what the half-life is. How long it takes to drop to 50% of your initial concentration. Okay. All right, so the half-life expression, which is what we're going to get out of this, is something that can be derived from the integrated rate laws. Again, I'm not going to necessarily go into the derivation of all of them, but you should note that this half-life expression is going to depend on a couple of things. It's going to depend on the rate constant, so K. It's going to depend also on the initial concentration of reactant species for some of these orders. But the most important thing to note is that the half-life expression is going to be different depending on if it's a first-order reaction, or if it's a second-order reaction, or if it's a zero-order reaction. Okay, and so we're going to go through the half-life expression for the various orders in the next few slides. Okay, so we're going to first again start with the first-order half-life expression. Just like I said a second ago, this half-life expression is going to come from the rate law, right? So I've taken the first order integrated rate law and I've kind of rearranged it here so that I have my concentration at time t divided by concentration of initial concentration. I'm taking the ln of that. So this is just another rearrangement of the first order integrated rate law. Okay, so now I'm going to set the concentration at whatever time we're looking at equal to 1/2 the initial concentration, right? So again, what is this half-life? So this is the time that it takes for this to equal 1/2 of the initial concentration, okay? So with that, that's essentially what a half-life is. So we're going to go ahead and utilize this, and we're going to substitute it in for that AT from above, up here, okay? So when we do that, we can cancel the A naughts, right? These guys are going to divide and go away, and we're left with this ln of 1/2 is equal to minus k times t. And again, this t with the 1/2, all this is denoting is this is the half-life. Okay, so ln of 1/2 ends up being a minus 0.693 is equal to minus k t, or half-life, right? Rearranging this, we're going to divide by minus k, divide by minus k, and we're going to be left with half-life is equal to 6.693 divided by k, okay? Which is what we get right here, nice and illustrated for us. Okay, so this is the half-life expression for the first-order reactions. Okay, so we have a first-order reaction. This is the expression that you would use to calculate the half-life, okay? A couple things to note about this guy, right? There is no dependence on initial concentration, right? There is no initial concentration in this expression at all, okay? So no, let me grab my eraser. We have no dependence on initial concentration. Dependence on initial concentration. Okay, and so that's going to have a very important little ramification. Okay, so if we think about what a half-life is, again, it's the time it takes for the concentration to drop to 1/2 its initial value, right? So for first order reactions, let's say we start at 150 torrs, so I guess this guy is in torrs as our pressure. The half-life, again, is the time it takes for it to go from 150 to half of 150, which ends up being 75, right? So this is the half-life. We'll estimate it to be about 12,000 seconds, right? Now, because this is first order, it will take the exact same amount of time to go from 75 to half of 75, which is 73 or 37.5. So again, the second half-life is another 12,000 seconds, right? It doesn't depend that this was less of concentration than this guy. Each half-life is going to again be the exact same value over and over and over again. This is unique for first order reactions. This is not going to happen for second and third, okay? So again, the half-life expression depends only on the rate constant and is independent of the initial concentration. Okay, so now what happens to second order and zero order half-life expressions? So it's going to be the same thing. The math here is the exact same. So I take my integrated rate law, I substitute AT is equal to 1/2 of A naught, because that's the time that we're looking for, right? And rearrange and solve for this time. And for second order reactions, I get this. I do the exact same thing for zero order reactions, and I get this, okay? So now for both of these, it's important to note that initial concentration does matter. So initial concentration is in both of these. So the half-life for both of these depend on the concentration, okay? But they depend on it in two completely separate ways, right? So if we look at the second order half-life expression, we have initial concentration that is inversely proportional. So inversely proportional to half-life, right? So what does that mean? As the concentration decreases, because this guy is inversely proportional, the half-life is going to increase, meaning it's going to get longer, okay? The big ramification for that for second order reactions is that as the concentration of the reaction decreases, the half-life actually starts to get longer and take longer overall, okay? Then for zero order reactions, instead of having this inverse relationship, the half-life is directly proportional to the initial concentration. It's proportional. I don't know what it is. Proportional to initial concentration, right? So again, it does depend on the initial concentration or the concentration of our reactant, but now it does so in a direct manner, right? So as the concentration starts to decrease, then the half-life will also begin to decrease, right? Meaning that as the reaction goes on, the half-life becomes shorter, right? So it starts to speed up as the reaction continues to occur. Okay, so those are the three half-life expressions. Again, they depend on the order of the reaction. We have first order, second order, and then zero order. This is a nice little kind of summarizing table that goes over these various rate laws, the integrated rate law for each one, for zero, first, and second, as well as the half-life expression. It also denotes the units of K for each individual one as well. So zero order overall has units of molarity per second, first order has inverse seconds, and second order has inverse molar inverse seconds. Okay, so I'm going to leave you with this question. I'm going to go ahead and make this question part of the quiz. A couple things I want to note about it before I go ahead and stop with it. So it says right here that we have a decomposition reaction, and it's a reaction that is observed, the rate is observed to slow down as the reaction proceeds, and it's found to have a half-life that depends on initial concentration of reactant, right? So what statement is most likely true for this reaction? So there's a couple of things that are important to note here. This part, that the half-life depends on initial concentration, notes that this has to be either a zero order or a second order. Because remember that the half-life expression for first order reactions didn't depend on the concentration, it only depended on the rate constant, right? So this was for first. It was zero order and second order that actually did depend on the concentration of the reactant, okay? So number one, it cannot be first order. It has to either be zero or second. So A says a plot of the ln of concentration versus time gives a straight line, right? So this would be what would happen if this was first order. We know that this can't be first order, so the answer cannot be A, okay? So now in B, it says the half-life of the reaction increases as the initial concentration increases. This indicates a directly proportional relationship, right? And then C says a doubling of the initial concentration results in a quadrupling of the rate. So this is just going back to the rate law. So this is just going back to, why is this doing this? Rate is equal to K, A to the N. So with respect to orders, which order would you expect to see a quadrupling of the rate when you double the initial concentration? Okay. So the answer is either B or C, but I'm going to have you figure out which one it is. Okay.